Okay. Right. So I know some of you already took a psychometrics course. So who didn't take a psychometrics course yet? Po-Sheng and Sarah and okay, Thomas and okay, the other students are all took it. So Thomas, is it required for your program in your program?
I think it might be part of the requirements. I just haven't taken it yet. I'm not 100% sure on that.
Okay. All right. Okay. So because the usually factor analysis is covered in psychometrics class. So the factor analysis is the exploratory factor analysis and confirmatory factor analysis, the both are the latent modeling approach. So it's very widely used in the psychometrics area. But PCA, we talked about the PCA, principal component analysis. Principal component analysis is a linear combination of observed variables, right? So this is dealing with observed variable, not latent variable. So the PCA method is very widely used in data science or machine learning because most of the data is more like the observed variable in the big data or machine learning or other multivariate. But in psychometrics area, if we, for example, survey data, right? Survey data is measuring the latent construct, right? So in that case, we maybe so the fact analysis would be more appropriate approach to analyzing the kind of data set. So okay, in this today I will overview the factor analysis. What is the factor analysis? How they are different than the principal component analysis, and then I will explain the how actually factor analysis works. Okay, so we'll show you the estimation process of the factor analysis. So you could have multiple options to run factor analysis. You can choose a maximum likelihood estimation or some weighted least square estimation or principal axis factoring. But principal axis factoring method is most commonly used. So if you run EFA, I think the 80% or 70-80% use a PAF method. But the MLE, maximum likelihood estimation, is also very good alternative. But in this course, I will focus on the PAF, principal axis factoring method. And then we'll talk about the R. Okay, overview. So in factor analysis, we present variables Y1 through YP as a linear combination of a few random variable F1 through Fm. Okay, so Y1 through YP, this is observed variable. This is your data. Okay, this is your observed variable. So that means your observed variable can be explained by the linear combination of your latent factor. This is called a factor. This F2, Fm is latent factor. Theoretically, it is possible to have the same number of factor as your number of variables. For example, if you have a 10 variable, theoretically you can have 10 factors, right? If you have 20 variables, you can have 20 factors. So these factors are underlying constructs or the latent variables. Okay, so these factors, the F, this is factor. This factor cannot be measured or observed directly, right? So for example, love, right? We can measure love by using some survey data, but we cannot directly measure or observe love, right? So this is the latent construct, okay? But height, weight, those kind of things is observed variable, right? So it's a height is height, so weight is weight. So we can directly measure using the physical measurement. So, and if the original variable y1 through yp are at least moderately correlated, so basic dimensionality of a system is less than p. So to run EFA, so to run the factor analysis or principal component analysis, so your observed variable should be correlated. Okay, so at least moderately correlated. If they are not correlated each other, I mean, there's no reason to run factor analysis or the PCA, okay? Because the PCA and factor analysis, those are based on the covariance metrics or correlation metrics. So using the correlation information, we want to extract common factor. So if there is no correlation among variables, you can find the good region, the results, okay? That's very important. So the goal of a factor analysis is to reduce redundancy among the variables by using a small number of factors. So the factor analysis is related to the principal component analysis in that both seek the simpler structure in a set of variables, right? So they are very similar, but they differ in many aspects. So, okay, first, so principal components are defined as a linear combination of the original variable, observed variable. Do you remember? So PC, this is the principal component. This is what? So your the coefficient. How can I say? So coefficient times. Let's say. I'm sorry. So your z equals coefficient times PC1, right? x1 plus x2, PC2, x3, and PC3, right? So these are all the x's. These are x, right? So and then your the principal components are defined as a linear combination of original variable, observed variable, but factor analysis is using F. Okay, so it uses the factor scores instead of observed scores. And in principal component analysis, so we explain a larger part of the total variance of the variable, which means, this means the principal components to use the full variance. So in principal component analysis, so total variance is equal to the common variance. Okay, I will show you. I will talk more about that later. Okay, so in CFA, principal component analysis, so total variance is common variance. That means it considers the total variance that has no error variance. Okay, it just assumes there is no error. Everything is a common variable. So every variance, every variable is perfectly explained by outcome variable. Okay, that is principal component analysis, but factor analysis is more realistic, right? Because your variables that cannot explain the 100% of your outcome variable. So the factor analysis take into account error portion. Okay, we'll see more example later. This is kind of overview. So orthogonal factor analytic model. So we assume a random sample y1 through yn from a homogeneous population with the mean vector mu and the covariance matrix y. So this is the first model by the Spearman, 1904, right? So Spearman, he developed the factor analysis, right? So he proposed this model. So first, if you look at this one, This is a linear combination. This is your observed variable, right? Y. Your observed variable is a linear combination of, this is the coefficient, okay? This is like the regression coefficient, okay? This is called the factor loading. And then F, this is factor. Okay. In the regression, I think Y equals AX plus B, right? This is a regression. So in the regression, X is observed variable, but here we use latent factor instead of observed variable. Okay. And then also it assumes it had some error portion. Okay. This is error. This is the variance that is not explained by your model, right? So this is the first observation. And then you can see we subtract mu1 here. So why do this? Because, which means that we are doing a mean centering. Okay, if you subtract the mu, it will be 0. So basically, we assume that we do a mean centering. So we just put the minus here. Okay, if you put mu to the right side, that will be intercept. That will be mean, right? So if you move this one to here, there will be intercept, but if you put here, it will be mean centering. Okay, so this is a typical factor analysis notations. Okay, all right. So the coefficient, the lambda, these are called the loadings. Okay, and also this is called, this is like the weights, the regression weights. Okay, so it indicates a relationship between your observed variable and the factor, and also magnitude between the observed variable and factor. Okay. All right. So this relationship can be simplified like this, right? Because Y is, this is what? This is your observed variable factor. This is a matrix notation, okay? This is your observed variable factor minus, this is mean 1, mean 2, mean 3, like this. And this is your loading, factor loading matrix. And this is your F, F1, F2 to Fn plus your error, like this. Okay, so this relationship, all these relationship can be simplified like this. Okay, so here, Y is, this is the response factor, observed variable. And this is your mean vector, right? This is the average of each the variable. And this is a factor. And then this is error, right? So, and then this is factor loading coefficient. Okay. So this is a simplified form. Any questions so far? No question? Is it clear? It's okay? All right. Can I move on? Yes? Okay. So here are some assumptions of the fact analytic model. Okay. So right here, y minus mu, this is equal to, what was that? Yeah, lambda f plus error, right? So this is our formula. So here are some of the assumptions. First assumption is expected value of each factor is 0. So factor is, this is a latent variable. Okay. For example, you measure the conscientiousness. Okay. So 1 to 5 Likert score, 1 to 5 Likert point. Okay. And then your scale is 20 items. And then you just summed up. Okay. And then the first observation got, I just make it number 19, 25, right? And 40, and 43, 27, 28, 29, and 30. Okay, this is the conscientiousness score. Okay, this is a raw score, right? But if you get a factor score of this construct, that is F score, that will be more like the standardized score. Okay, so will be like minus 1.4, 1.3, I don't know, so 0.4, 0.5, 1.6. I just made it up, okay? Like this. So this is observed score. But if we get a factor scores from the latent trait modeling, the factor scores mean is 0. So which means this is your data. This is your data value, and the mean is 0. Okay. So in this case, I'm 2.5. His score is 40. Observed score is 40, but my data is 2.5, which means okay, this is data is 2.5. He has a very high level of conscientiousness. Okay. So this is a factor score. So factor score follows normal distribution, multivariate normal distribution. So it's a mean of a factor score is 0. And let's say you have two data sets. One is for male and one is for female. And then you get the factor score, you estimated it, and then you get the factor score. So one factor score is for male group, and another factor score is for female group, okay? And the factor score for male and factor score from female. Can we compare these two scores, like the t-test? Which group is higher or lower? Can we do that? Do you think that we can run t-test to compare these two factor scores between male group and female group?
Yeah.
Shay say yeah.
Probably wrong.
Any objection?
Like a measurement and variance test? Is that...
Okay, let's think about that. We have a male group, right? And then we estimated it. And our data will be 0, right? Mean of data will be 0. In the female group, also data is 0. Right? So we cannot directly compare these two because this data, the mean of data is only for the specific group. So how can we compare these two groups? We have to put those scores on the same scale. So which is called the measurement invariance. Okay. I'm not sure you guys follow me here. You follow me? Okay. Yeah. All right. So let me. This is kind of side.
So
Yeah,
you mean
Shay.
if they're estimated together and then you group them as opposed to estimating one group factor scores and then estimating another in two separate analyses?
Yeah, so there are two different approaches. Oops, we're okay. Give me a second. Let me. Okay, so the first, this is male, and this is a female. We have to put them on the same scale. Okay, so which is called the multi-group analysis, multiple group analysis. Okay, we need to model it. We need to make a model, both of them. Okay. Well, by doing that, we can put their scores on the same scale, and then now we can compare apple and apple. If you separately estimate, because the mean is almost always 0, right? And then you cannot directly compare these two. Anyway, their mean will be 0 because their mean, their scores will be scaled on that scores. So the first approach is you need to estimate two groups in the one model. Okay, that is a multiple group analysis. The second approach is you estimate one group first. Okay, they estimate one group first, and then you put the scores on the other group's scale, which is called the linking method. Okay, this is more advanced topic, so I will just give you the idea, okay? So you cannot directly compare two groups by separately estimate cases. Okay, and then second assumption is the total variance of each factor is 1, and the factors are uncorrelated. Okay, this is the second assumption, which means, okay, total factors, total variance is 1, and they are 0. Okay, so factors uncorrelated each other. So this is identity matrix. Okay, this is second assumption. And then third, expected value of a residual is 0, right? This is the same as regression analysis, right? So the expected value of a residual is 0. So using these assumptions and one more assumptions, so we do have some residual part, right? So this residual part represents the part of the variable that is not in common with other variables. So which means this portion is not explained by other variables or by the model. So this is error portion. Okay. So this is the specific variance. So this residual variance is, this is the covariance metric of residual variance that we say psi here, and psi 1 through psi p. This is residual variance. And then all the covariance of residuals will be 0. So we assume they are not correlated each other. Okay, so they're all 0. So this is residual variance matrix. Like this. And covariance between the variance of a y residual is unrelated factor. So your factor score and the error is not related to each other. Okay, this is same as regression analysis. Think about the regression analysis. So your observed variable is not related to your error, right? And also error is not related to each other. It is same assumptions here. Okay. If your errors, for example, if your errors are related to each other, the what assumption is violated in that case? Independence assumption, right? So we assume each individuals are independent. But if their errors are related to each other, their data is dependent on the other data set. So they are not related, they are dependent, right? So we assume the correlation or covariance of error variances are equal. So assumption made above is the simple explanation of the variance of y here. So this is the variance of y. So variance of y is a linear combination of each coefficient square, sum of squares of each factor loading. This is coefficient, right? Regression, like a regression coefficient. Each coefficient, if you square it, and then this is what? This is error variance, residual variance.
Wait, so that error variance is only related to that first variable, so like that that's like that individual variable's error variance, as opposed to the
So
other error term that we were talking about earlier.
This error variance is a matrix, like the x1, x2, x2, xn. So is that what you're saying? So
Yeah, kind of. Okay.
yeah, so this is y1 square, y2 square, y,
Okay.
n square.
Okay. Perfect.
Yeah. So in the fact analysis, right? So we seek to express the observed covariance matrix. So this is covariance matrix, and covariance metric is like this. We see this, right? So this is the loading, factor loading matrix. And the F is, this is the factor score, factor, and this is error, right? And the loading part and loading and factor score and the error, they are unrelated. Okay, we assume they are unrelated each other. So this equation can be decomposed as like this. I mean, you don't have to memorize anything here. I mean, it just helps you understand the logics behind the fact analysis. Okay, so these two are independent. So we can make a covariance matrix of loading and F plus error. So this part looks like this. And then this is error variance. And then mathematically, they can be transformed like this. And this is the final results. Okay, so what you need to learn, when you need to remember is, okay, so covariance matrix is, which means this is factor loading matrix, right? So loading one, for example, x1, x2, x3, x1, x2, x3, and loading 1, 1, loading 1, 2, loading 1, 3, loading 2, 1, 2, 2, 2, 3, right? So we can have some factor loading matrix. So that is a factor loading matrix. And then if you transpose it and plus error variance, that is the covariance matrix. Covariance matrix of factor model. Okay, So the factor loadings represents, okay, what is factor loading? Factor loading represents the covariance of the variable with the factor. Okay, so do you have, this is your observed variable, right? And this is your factor. So for example, in your regression coefficient, just think about the regression. Y is your outcome variable and X is your independent, right? The relationship between these two is what? This is a beta, right? Coefficient, right? If you run a single regression, the coefficient of X is a correlation, right? So this is the beta in the regression. Beta is the relation between outcome and predictor. So it's the same. The factor loading is the relationship between your variable and factor. Okay. So yi is equal and lambda 1 plus f1 plus lambda 2 f2 plus lambda 3 f3 plus error. Okay, so let's say we have three factors in this case, right? We have three factor loadings. These are all the coefficients, right? Regression coefficient. So this regression coefficient is the relationship between y and first factor. This is lambda 1. What about lambda 2? This is the relationship between y and second factor. This is lambda 2. And this is lambda 3. Okay. If you use covariance matrix, and then this relationship will be covariance. But if you use a correlation matrix, it will be a standardized relationship. And the covariance matrix, the y and f, the f is a factor, and a y is observed score. And then this is the factor loading. And then we partition this matrix, the covariance matrix, into two parts: communality and unique variance. Okay. We partition the variance of y, So this is the y1 square, y2 square, y3 square, right? These are variance, and these are covariance. But we partition these variances into two parts: communality and unique variance. So this is variance, same thing, because we multiply II twice, same thing. So this is a variance of yi, and this is first the factor loadings square and the second factor loading square to the last factor loading square plus residual error. Okay. And then this part is h square, which is called communality. Okay. And this is called error, specific error variance. Right. So let me give you another example. Maybe you can think. You learn about the R square, right? So what is R square?
Commonality.
Communality, yeah, communality. But I mean,
Shared variance among.
yeah, sure. I mean, the more easy, using more easy language.
Variance accounted for.
Yeah, variance accounted
Percentage
for.
of variance accounted for.
Right, right. Percentage of variance accounted for by other variable, right? Predictors, right? For example, y equals x1, x2, and x3, right? Okay. And then let's say we have some A, B, and C. Okay. These are our beta. coefficient, right? So this is a coefficient case, right? So if you square the coefficient, it will give us some R square form. Okay. Y equals AX plus B. Let's think about the single regression coefficient. You standardize it. And A is correlation. This is correlation, actually. If you square it, that is R square. If you square this coefficient, that is R square. The same thing. If you square the coefficient information, that will give you the common variance information that is explained by x1, x2, x3. Okay, how much variance is explained by x1, x2, x3? Okay, you can square these coefficients. It's the same thing here. If you square the factor loadings, that will give you the commonality. Okay. So how much of your variable is explained by each factor? If you have 3 factors, this variable, the 72% of this variable is explained by 3 factors or something like that. And that this is why it's a unique variance. And this is, so this common variance is called communality. This is communality. Okay, this is H square and the communality and specificity. So the variance of Y, the variance of your outcome variable is equal to communality plus the error variance, specific variance, right? So this is like the R square plus 1 minus R square is 1. So do you follow me? Okay, so here is a fundamental difference between PCA and fact analysis. So do you remember the sequence of PCA analysis? We centering the variables, right? We mean centered and standardize the center. So we standardize the variables. So 0 and 1. So we can make correlation matrix. And then from that correlation matrix, we extract the eigenvalue and eigenvector, right? So the correlation matrix is 1, 1, 1, 1, right? So variance of this correlation matrix is what? It's 1, right? Which means it has 100% variance is here. But EFA using commonality part. Instead of 1. Okay, we use this part. I mean, if you add commonality and error portion, it will be 1. Right? But EFA at the fact analysis using this part, only commonality part, which means we remove some unexplained portion of our data set. This is a more realistic approach because the variance of our the variable cannot explain 100% your variance. So instead of using 1, we are using commonality. Does that make sense? Okay, so here's an example, the fact analysis. Let's say we are measuring, so reading, we have reading scores and writing scores, okay? And then I just get the average, aggregate the scores, the reading and writing. And then you can think, okay, through the reading and writing, we can measure some latent variable, latent construct, right? So we say this is a language skill, let's say. Okay, so language skill explains reading and writing. This will be factor loading. 1, 1, and factor 1 and factor 2. Let's say this is 0.9. And if this is a 0.1, what does it mean, 0.9 here? So the factor loading is the relationship between factor score and observed variable, right? So which means the 0.9 is a very strong relationship between language ability and reading. Okay, and but if this is a 0.1, I mean it should be highly correlated each other, but I just say 0.1. That means okay, this language ability factor does not predict writing. Okay. So these two are not related to each other. So this is the factor loading. So again, factor loading. Factor loading is the relationship covariance over correlation between common factor and observed variable. So this is what we want, right? This is a true relationship between these two variables. So if you add these two things, that is common variance. So right here, this is common variance. And then factor analysis also consider error portion. Okay, this is a unique variance. Okay, so this will be 1 minus lambda and 1 minus lambda 2. Because total variance is 1. Right? And this error includes systematic error or non-systematic error or measurement error, any kind of a measure, the errors that can be included in this error. Okay. So the error variance, the unique variance, if you add these two, this is total variance. Okay. Question?
The total variance here is 2, correct?
Correct.
Okay.
Yeah, total variance is 2 in this case. If we use the correlation matrix.
If we use correlation measure. Okay.
Mm-hmm. Yeah. Any other questions?
Would there be a difference, like we using the covariance matrix and the correlation matrix? Will they always give me the same results?
No. So the variance will be same, but like the R square, the basic information will be same, but this will be different. The loading coefficient coefficient will be different.
Okay, only the loadings will be different.
Yeah.
And that's only affect my interpretation.
Mm-hmm. Right. But usually we need standardized coefficient, not unstandardized coefficient, because it's much easier to interpret, right? Because if the reading score and the writing score have different scale, we cannot directly compare these two factor loadings.
Okay, so we usually prefer correlation matrix.
Yeah.
Okay.
If you run it, most software package, if you run SPSS or R or M+ program, it will produce the unstandardized result. And then also the standardized results. Okay, so most software produced both results, unstandardized factor loading and standardized factor loading. Okay, So, but it doesn't say how this get results. So this result, unstandardized result, is from the covariance matrix. But standardized result is the correlation matrix. Correlation matrix. But we usually report standardized correlation, the result. But some study reports the unstandardized result, but it's up to you. Any other questions before we move on to the factor axis, principal factor axis factoring? Okay, good. So I will, okay, let's see. Now let's talk about the estimation of a principal axis factoring. I will show you how actually factor analysis works in your program, in your computer program. Okay. So this is like I said, principal axis factoring is one of the most commonly used factor analysis method. So let's review the PCA algorithm one more time. So PCA, the first we do a mean centering and then get the correlation or covariance matrix to compute the eigenvalue or eigenvector using the covariance or correlation matrix, and the order the eigenvalues and corresponding eigenvectors. And then for, let's say if you have a 5 variable, we have a 5 eigenvalues. So first eigenvalue will have the largest value, right? The second eigenvalue will have a second largest value, and to the 5th. And then also we can have the eigenvector for each corresponding eigenvalue. So in that we can compute Z. This is this is principal component, right? So, and then here, these are what? This is eigenvector information, right? So we talked about that one. Okay, so we need to start from here. Here is an example. We have 10 students, and then we have a reading score and writing score. There are some scores. Okay, and then here is a mean, and here is a mean, and here is a variance, here is a variance. But they say they have the same mean but different variance. I just made it up, so it's a really simple example. Okay, so first I got the correlation between these two. So this is reading and this is writing. Okay, diagonal is 1, and this is correlation between reading and writing. And then using this correlation matrix, I got the eigenvalue. So my first eigenvalue is 1.98, and second eigenvalue is 0.02. Okay, and then also I can get eigenvector, corresponding eigenvector. It's right here. Okay, and then I can get the PC scores, right? Using the Z equals the PC 1 plus like that, right? So here, what I used is the correlation matrix here. So the variance of this correlation matrix is what? 1, right? Okay, so common variance this is first variance plus second variance is what? That's 2, right? So from this correlation matrix, the first variance and second variance, if I add these 2 variants, that is a common variance. That is 2. And then if I add eigenvalue, I have 2 eigenvalues. if I add these two eigenvalue, this is total variance actually. And if I add these two, what is it? This is 2, right? So my total variance is equal to the common variance. So because the variance of my correlation matrix is 1. So all the information is used in the correlation matrix. Okay, so this is PCA. Okay. So in PCA, the total variance is equal to common variance because this is the common variance plus error variance, but there is no error. Error is 0, so everything is a common variance in this case. And now let's estimate the commonalities from using the factor analysis. Okay. So the first step is to find R square. So we have 2 variables here. So I will get the reading. I will treat the reading as my dependent variable, and the writing is my independent variable. Okay. Run a regression. And they got the R square value. Okay. And that R square is 0.96. Second, okay, this is the first. And second, I treat the writing as a dependent variable, and then reading as an independent variable, and run it. Regression analysis, and I will get another R square value, right? That R square is 0.96. So this is R square for second case, right? So actually it's the opposite, I'm sorry. So it should be writing, it should be reading. So it's the writing. This is our IV, DV is reading. Okay, so anyway, so you got that, right? So we run regression analysis and we got the R square value. And this R square value is very similar to the commonality because, you know, by definition, R square looks like this, right? R square is 1 minus sum of squares error over sum of squares total, right? So sum of squares error over sum of squares total, this is what? This is the residual variance, right? Error variance, residual variance, right? This is total variance. If you subtract the residual variance from the total variance, that you will get the R square. That R square is a commonality. Okay. Any questions so far? No? Okay, then this is our original correlation matrix. So now we replace our variance by R square. Okay, so this is commonality. Okay, so in this case, it was 1, but now we are using 0.96, right? 96% is common variance. What about the 4%? Okay, so that means we removed the error portion, the 4% of error from our commonality. So which means, okay, this is more realistic, right? Because 100%, the 1 means everything is a common variance. There is no error variance, but this case is 96% commonality plus 4% error. But we do not add error portion. We'll only consider commonality because the error is noise, right? So this is the error variance. So we replaced the variance by R square. So this is commonality. So this is a fundamental, the difference in idea of principal axis factoring. So there are a couple of different estimation methods. So the first one is principal axis factoring. This is the most commonly used method in the factor analysis. And it uses correlation and covariance metrics. And its initial values in iteration is important. So it uses iterative algorithm. We'll see that. Okay, and this is the iteration of SPSS default is 25, or other the R also 25. Usually the default is 25. Sometimes you may have some non-convergence issue. Okay, your estimation will not be converged appropriately. In that case, you need to increase the iteration process. We'll see that later. The second, the maximum likelihood estimation. We assume that our observation follows the multivariate normal, and then using the maximum likelihood values that we try to estimate the maximum likelihood value for each parameter. This is similar to the regression method, okay? But it used the EM algorithm. So E is expected, M is maximized. We expect our initial value, and then we maximize the log likelihood value, and update it, and then maximize again, update it, maximize it again, update it, maximize it again. And if we do not have enough, if you do not have the big difference, if you have only negligible difference between these two processes, and then we stop. Okay, it works for the largest sample size. The maximum likelihood estimation is also very commonly used for the factor analysis. And then unweighted least square, generalized least square, I never used it. So, but we do have a couple different options. Okay, so mostly we use these two methods here. Okay, let's go back to our example here. So the PCA, like I said, PCA use commonality, right? This commonality, how can we get this commonality from our example? This commonality is what?
0.96.
Yeah, 0.96. What? That is what?
R square.
Yeah, that is R square, right?
Mm-hmm.
So we are using R square value. Not that means we replace R square by we replace 1 by R square value. So and PAF estimate parameter via iteration the process. So we use the initial value of a commonality, and then PAF updates new commonality variable, and then compare difference between these two commonality, and update it, and compare, update it, and compare, update it, compare, and then this iterate stops until the difference is less than 0.00001. This is default. So SPSS number of iteration is set to 25. So R, I think that R is also 25. So if you have the non-convergence issue, you need to increase this iteration process. Let's more talk about this process. So, all right, iteration, we have 14 minutes, I think, okay. You need to listen carefully because it's pretty confusing. Okay, this is our original, the correlation matrix, right? We start from there. And then we got the correlation, we got the R square. So R square was a 0.96 and 0.96. And then we replace it, right? So this is our initial covariance matrix. Okay. So, and then this R square is commonality. This is called commonality, right? 0.96, 0.96. This is commonality, right? Okay, so iteration step 1. This is iteration step 0. We got the new covariance correlation matrix. And then iteration step 1, this is updated R square, right? And then we got the eigenvalue and eigenvector from this matrix. Using this matrix, we can get eigenvalue and eigenvector, the first factor and second factor. And these are eigenvector for the first factor. These are eigenvector for the second factor. Okay. And then now we will get the factor matrix. Okay, so this factor matrix is eigenvector times square root of eigenvalue is factor loading. It's right here. It's the 0.707. This is eigenvector times the square root of 1.94. This is square root of eigenvalue, right? And the same. Which way is that? And a 0.77, this is second eigenvector. I'm sorry. Yeah, second eigenvector. And then negative 0.1. Okay, that is the 0.98 and a 0.98. This is this is a factor loading. Okay. And the second one is this is almost 0, right? So if you have a negative value, eigenvalue, so there is a negative value, it's just a fixed 0. If you compute it, its value is really close to 0, negative 0.000 something. So we just treat as a 0 here. So this is what? This is a factor loading. This is a second factor loading. So the first factor loading square plus the second factor loading square, that is 0.97. This is communality. Okay. And then same here. So 0.98, this is factor loading, 0.98 square plus this is 0, a 0 square. The 0.97, this is communality. And then we update our communality. This is our original communality, right? This communality is from here. 0.96, 0.96, this is original communality. And then we just got the updated communality, 0.97. And then we got the difference between these two communality and score it. And add difference and score it. And that is 0.000196. So we want this value is less than this criterion. But this value, this difference is still greater than our criterion. Okay. And then we repeat this process one more time. I will talk about this one in the next class. And then one more time, but it doesn't reach our criterion. And do it again, and still. And then now it satisfied our criterion. So we stop it. And then final result is the factor loadings. Okay. I just overview this process because I don't think I can finish this one today. So this is the general process of a PAF. Okay. Any questions?
The communality is always increased during the iteration process, right?
Yeah, right. So if you do the iterate, communality is always increase.
Okay.
But how much increase? We don't know, right? So we'll see more example later.
Okay.
Phil, is there ever a benefit to using a different like approach, like maximum likelihood? Or do they render different outcomes ever, like in really weird situation?
Yeah, it's like the maximum likelihood estimation, usually it works well for the large sample. But if your sample size is pretty small, I would rather use the principal axis factoring. But I compare I mean, when I run the EFA analysis, I run both and I compare the result. Usually they're very close each other. So yeah, maybe sometimes you try the PAF and you still have some convergence issues, and you keep increasing the iteration, but you still have an issue that you definitely have to try maximum likelihood estimation as an alternative. And sometimes it works in other estimation method. So, but generally they're very similar. The value is similar. Yeah. Any other questions? Okay, so I didn't finish PAF iteration process, but I will finish that in the next class. Okay, today we talked about EFA and fact analysis, right? So now you see what is the fundamental difference between the fact analysis and principal component analysis, right? So principal component analysis, in principal component analysis, the variance, total variance is equal to the common variance, because it treats all the common variance is a true variance, the total variance. It doesn't take into account the error portion, right? Sometimes if your reliability of your measurement is really good, in that case, that makes sense. But if your reliability is really poor, which means your data actually has a lot of error portion, but you just treat that data as a perfect data and then run PCA, in that case, your result will be biased, right? So in that case, definitely you need to use the fact analysis. But fact analysis is more commonly used in psychometrics area, but I don't see many cases in data science or machine learning case. So in those cases, so the PCA is most commonly used because most of the data is more like observed data, not latent variable data. Okay, so this is the main difference between these two approach. And then next class, I will finish the algorithm and some rotation, understanding of rotation, fact rotation, and then we'll show our example. Questions?